Sorry, dealing with some technical issues there. So, didn't receive any questions in advance. Typically true this time. We got exams going on for Orgo 1, Orgo 2, and just got done with the exam for Chem 2. For Chem 2, the goal is to get you the exams back Wednesday, but I got a person that needed to make it up remotely. So you may not get them back Wednesday, just depending on when they're able to come in and like take their makeup exam. But other than that, you should be getting your exams by next week. That's about it for what I have in terms of announcements. I've got the chat open in case you got any questions. I'm going to get some work done, particularly to update the homework for Organic 2. There are questions I want to get rid of. But again, these are office hours. These are not lessons. These are not lectures. So if you got questions, please post them in the chat menu and I'll answer them. Keep in mind there's about a minute lag on my end today, so it's going to take me a little while to get back if you type it, but I do get back to your questions in the chat. All right, got asked if I can go over the R and S notation on, this is for Organic 1, and this is the test material, and it is page 15. All right, so R and S notation with alkanes is the hardest and honestly most obnoxious. This comes from the fact that there are no heteroatoms. And so what we do to identify R and S is we use the Kahn-Ingold-Prelog rules or the CIP rules. And these CIP rules assign priority by atomic weight. Well, if you've got a molecule that's composed primarily of carbon and hydrogen, you're basically looking for a situation where you have a branch or you have a termination, and this is really what sets the RS. So let's start with this one. And there's two ways to do this. You can do the strict CIP rules, which are, and I'll start with those first, where we start going through and we look at what's bound next to the atom we're considering. And I'll talk about a shortcut to do with alkanes. So if we look at this center here, we've got a hydrogen going back, we have a CH3 group here, a CH2 group here and a CH2 group here. Hydrogen is the easiest to assign with the lowest priority of 4. So the question is, we've got 3 carbons, which of these carbons is the higher priority? So what we're going to do is we're going to write out the elements that are bound to it. So this methyl group has 3 hydrogens. This carbon has the next carbon and 2 hydrogens. And this carbon has the next carbon and 2 hydrogens. And we're going to arrange this by descending atomic weights. And we see that this has the hydrogen, so this one's the lowest priority relative to these two, so this would be priority 3. Now if we work to the next carbon, this carbon has that carbon, and a hydrogen. This carbon has the next carbon, hydrogen, and a hydrogen. So the first point of difference, this ends up being the higher priority, so this makes this the highest priority group on this carbon, and this one the second lowest. So yeah, there's a lot going on here. Now, mercifully, the hydrogen here is pointed back. So we've got the lowest group pointed back. If we look at this, there's 1, 2, 3. This is a clockwise rotation. So this would be an R symmetry for this particular group. Now, I grab those next. Now, what about this carbon? So we got this one as R. It's going back, and we've got the propyl chain. And in this case, we have the hydrogen coming out at us. So again, hydrogen here is going to be the lowest priority, but we've got a carbon, and a carbon who ends up taking the higher priority. So this carbon is bound to another carbon and has 2 hydrogens. This carbon is bound to another carbon, 2 hydrogens. This carbon is bound to another carbon and 2 hydrogens. So first step out, we don't really see a priority. And I'll get to the Orgo 2 question in just a minute. Ethyl group, it still works out, and we'll talk about the shortcut. Yeah, you're right. There is an ethyl group. That would just take you one more out. It's still going to end up being the same priority. I'll talk about how I know that so quickly. So now, next I'll take a look at the next carbon. So this is a carbon, 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 hydrogen, carbon, 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 hydrogen, hydrogen. This step out puts us carbon, hydrogen, hydrogen. So this will end up taking the highest priority of these 2 chains. It's the first point of difference. Now we have to go one more out. Carbon, hydrogen, hydrogen, hydrogen. And this one goes full circle. So this ends up taking the second priority because this one terminates in hydrogen. So this is the third lowest priority. So a lot going on here. But at the end of the day, this is highest priority direction, second highest, third highest, lowest. Now, there's 2 ways you can consider this. If it doesn't confuse you, if the hydrogen's sticking out, you just reverse the RS. So since it goes counterclockwise, but the hydrogen's sticking out, this would end up also being R. The other way, which I actually advocate to, is for you to actually build the model and flip it. So what's a faster, more rapid way of doing this? For CIP, there is a consequence of alkanes. The first to branch is higher. The first to terminate is lower. So if I look at this carbon, I've got the hydrogen going back, so it's lowest priority, and then I've got carbon chains coming out. So if I start working my way out, so I've got this carbon, this carbon, this carbon, nothing has happened. This carbon terminates first, which would make it the lowest priority relative to these 2. So this is automatically priority 3. If I go this direction, it branches first, which makes it higher priority than this direction. So this would end up being 1 in 2 directions. So there I am able to get the R back. If I look at the other carbon, So hydrogen here, mercifully lowest priority. And as I start working my way out, this branch terminates first relative to these two, so this ends up being lower priority. And when I look at these two directions, this ends up I hit the first branch when I go counterclockwise versus where I go clockwise. So this will be the highest priority, and this will be the second lowest priority. And again, that's where I get the R and S from. And I can use that for the next one as well. So if I start with this carbon, hydrogen's lowest priority. This terminates first, so it's the second highest. These two, they both branch at the same time, but this one has the bigger branch. So this takes second priority, or first priority, and second priority. So once again, now that 1, 2, 3, this still maintains an R configuration. If I look at this one down here, so hydrogen comes out, lowest priority. This terminates first, so this will end up being the third because I go 3 carbons out, it terminates. These never terminate. If I go opposite directions, this branches first, so this will take the top priority. Counterclockwise branches second, so we'll take the second priority. This will actually end up giving me the S conformation. 1, 2, 3. It looks clockwise, but because we have the hydrogen coming out, it actually ends up flipping. And if we look at this one, hydrogen's lowest priority. The methyl group definitely terminates first, so it'll end up being second lowest priority. If we go counterclockwise, this is where we encounter our first branch. So this will end up being the higher priority direction. This doesn't branch until the second carbon, so it'll end up being lower priority than the counterclockwise direction. So we have 1, 2, 3 with the hydrogen pointing back. So this gives us the S conformation as well. So with the CIP rules, learn them correctly with a whole like working your way out. That said, alkanes are the hardest to learn, they're hardest to do for R and S notation by sheer merit of the fact there are no heteroatoms. And so there's actually a couple shortcuts we can use. If we look at the 3 direct, so hopefully we have hydrogen pointing out. But if we're comparing alkane directions off of a carbon in an alkane, whichever direction terminates first, that's going to end up being one of the lower priority ones, especially if the other two keep going further and further. If we have a ring, or even if we have a branch, the first one to branch ends up taking a higher priority relative to the other ones. So in the case of this one, when we went counterclockwise, this branches on the first carbon, number 1 carbon. This one branches on the number 2, and that's why this ends up being a lower priority direction, because the first branch creates a higher priority. And that's how I do alkanes. All right, problem 78 on the Connect homework. For Orgo 2. Okay, so lithium aluminum hydride. We're going to cover this more when we go to the next unit. It's not that bad of a molecule. So next week you'll be working with sodium borohydride, and so sodium borohydride and lithium aluminum hydride are kind of like sister compounds from a synthetic standpoint. But this is the overachieving sibling, and this is the one that kind of like much more chilled. So what do I need? So sodium borohydride, this will reduce ketones and aldehydes and convert them to alcohols. So, but that's all it can do. It's not a particularly aggressive one, and because it's kind of like the more kind of laid back reagent. We actually work with it in the lab because it's not terribly reactive. It does a good job of what it's doing, but it doesn't like immediately react with water. Lithium aluminum hydride immediately reacts with water, and it converts ketones, aldehydes, carboxylic acids, esters, and I think it will even do it with ethers, but it converts them to alcohols. So it is a super aggressive reducing agent. This is why it's not air stable, and so lithium aluminum hydride, you typically have to work with it under air-free conditions because it will take any bit of moisture and produce aluminum oxide and lithium hydroxide and hydrogen gas. So example page 3. Okay, so I'll get to that one in just a minute. So as far as the first step for what it's showing you, all we're going to do is take our carboxylic acid here and convert it to an alcohol. And then my guess for the sodium hydroxide, and this is consistent with that molecular formula, C3 ClO. For the, I'm guessing with the, oh, it's an alcohol. We'll do an elimination, but what type of elimination are we doing? Oh, okay. So this is an epoxide. And then for the hydroxide, all we're doing is doing our epoxide elimination. You end up creating two forms of this epoxide. So we'll take the hydroxide, this will pop off the chlorine. Think about a little, well, first of all, this isn't a chiral carbon, so we don't really have to worry about the stereochemistry. This is a chiral center, and since we're doing this under basic conditions, we're going to have an inversion of symmetry. So what will happen is this hydroxide will turn over. Sorry, this alkoxide will turn over. And when you finish reacting the bridging oxygen with the chlorine, you'll see the methyl group come up, the hydrogen up, and the chloride pop off. So actually, this is a really good problem. So you first have the lithium aluminum hydride, H4. This is going to completely reduce the carboxylic acid to an alcohol. The hydroxide here is going to form the alkoxide. The alkoxide, the oxygen actually has to rotate over. You're under basic conditions, so you're going to get an inversion of symmetry here. And it will come up, pop up the chlorine. And when you draw your final answer, you do need to keep the stereochemistry in here, where you've got the wedge coming out, and you've got the epoxide ring pointing down. Example 3 on page 24. Yeah, so for this one you're producing, this is just a combustion reaction. The example here is we have cyclohexane plus oxygen, and it combusts to CO2 and water. And so, yeah, you just need to, reactions of alkanes are incredibly boring. There's only 2 reactions they're going to do for our course. Free radical halogenation, which is super hard to control in practice, so we teach it to you more as kind of an example. This is definitely not something people like to do in the real world. But it does introduce this idea of primary, secondary, and tertiary carbon atoms and quaternary atoms. So with the reactivity with free radical halogenation, we ideally get mono substitution, and you only get it on the most substituted carbon. In practice, it substitutes everything it can. And the other reaction we're going to cover is just straight combustion. It's ring, it's whatever your hydrocarbon is, combusting to CO2 and H2O. The easiest way to solve these, write out the formula. So C6H, if it were linear, it would be 2, 6, twice 6 plus 2, but we've got 12 hydrogens because of the ring. So O2 is 2C. And this you can pretty easily balance. Now, cool fact we learned while we were trying to write the final exam. Saturated alkanes, there is never a number in front of here. It's always 1. This isn't true with alkenes. With alkenes, you actually you can create scenarios where you have to put like a 2 or a 3 in front of here to make the reaction work out, because the oxygen shouldn't finish with a fractional number. But with alkanes, when you work it out, oxygen, this leading molecule, never has to be anything other than 1. The only things you really have to balance are the oxygen, the CO2, and the H2O. How the stereochem work for Simmons-Smith and epoxide ring opening. So we'll start with Simmons-Smith. Simmons-Smith is not stereoselective. And this is going to be true of any addition to an alkene. It's trigonal planar. So let's create our hypothetical chiral molecule. What we'll do is we'll do the Simmons-Smith. And with Simmons-Smith, this is your CH2, I2, zinc, and I think there's something else in there. So we're going to get both stereocenters here because this is a trigonal planar molecule and there's no favoritism for one or the other. So we'd end up having to draw it 2 ways. One where we added it to the top, and one where we added it to the bottom. And the reason being here is that it's not stereoselective for, we're going to find this for a lot of alkene reactions. There's just no way to make it add preferentially to one side or the other by sheer merit of the fact that it's planar. There's no preference for one side or the other. If you flipped it over, there's no driving force here. For epoxides, it's the same thing. So if we did RCOOOH, we're going to get the same thing. We're just going to have the oxygens in here as well. So we'll end up generating a mixture of both. Well, let's say that's R and S. We'll also have the S and the R. The trick to drawing these quickly or working out the products quickly, you're either going to push these up or down. So the only rule here is if they start cis here, they have to finish cis. And I hate using that term, but because we have no ability to rotate within the ring, we can still use that term, because this group and this group are cis here. They also have to be cis on this side as well. But to save ourselves a little bit of trouble, we can make them both these both wedge and these both dash, and draw the ring pointing up and the ring drawing pointing down. And then if you want to flip it, you would see that if you were to rotate this over, you would end up getting their wedges and dashes flipped. But again, they're cis here because they're cis here. These are trans, therefore they have to be trans on this side as well. For organic lithium, does it always have to be chlorine attached to carbon chain in order for it to be replaced? Would it still work for other halogens? Yes. Actually, iodine is the best leaving group, so if you really wanted to guarantee this reaction worked with good yield, so we have some halogen here, X, and what we ultimately want to get to is this structure here. In terms of reactions, so if you did fluorine for X, this wouldn't happen. And chlorine, bromine, and iodine. So iodine would be the best leaving group because it's the largest. It's better able to distribute that -1 charge. So we always finish with -1. Iodine's a very dispersed atom. The trade-off here is that we have our competition with SN2. So you have hydroxide here. The other thing it can do is it can go in and it can start substituting. And so it's also going to be better at substituting them as well. So chlorine's going to go as the slowest, but it's also going to have the best selectivity against SN2. Iodine's going to go the fastest. It just also has the worst selectivity against SN2. So as far as naming epoxides, that's kind of outside the scope of this, my class at least. I think the ring is called oxyrin, which is this molecule here, and then you would name it based on the functional groups, and you'd have to add the R and the S's. So if we had we need to memorize, so we'd have methyl. Ethyl comes before methyl. Isopropyl. And since ethyl's coming first, you want to put it there. So it would be 1, 2, 1, and then you need to do the stereochemistry. So 1, 2, with, oh goodness sakes, this one's going to be the easy one. So that's lowest priority, highest priority. This will be the second highest priority because it's bound to the oxygen. So 1, 2, 3. This would be 2S. And then if we look at this one, the methyl group is lowest priority, top priority. This direction is the second highest priority, third priority. And so 1, 2, 3, clockwise, we'd have the 1R, 2S, 1 ethyl, 2 isopropyl, 1 methyl oxyrin, as well as the other 1S, 2R, 1 ethyl, 2 isopropyl, 1 methyl oxyrin. But we're not going to name the epoxides. And the big reason is that it's kind of esoteric. Epoxide chemistry is interesting, but it's kind of niche. I was talking with a coworker about it yesterday, and I asked about like naming epoxides, and even he kind of took the attitude as like, there is a naming scheme for them, but it is such a niche field of organic chemistry. You're not really, it's not that good to, it's not that beneficial to learn it. So the field of organic chemistry is actually, so your undergraduate degree in chemistry is kind of a survey degree, and that is a good thing. I don't say that disparagingly. It is a survey degree because the idea is that when you step into the workforce, you're going to be specialized. So it's good to know everything because you need to have a broad understanding of everything because you never know where you're going to land. You could do QC, QA, quality assurance, quality control. You could go into research. You could be a bench chemist. And you could do inorganic chemistry, organic chemistry, analytical chemistry. There's a whole set of things that your degree is basically a foundation for. We're on 17 looking at homework. But the thing is that organic chemistry is a huge field. So is inorganic, analytical. There's lots of them. And so you can that's what PhDs are for specializations. And so we have to decide as instructors at this level, what is an appropriate level of depth, knowing that we don't want to omit anything because it might be useful, but we also don't want to go too deep because there's no point in learning it if you don't use it. Ooh, okay, so this is actually a nice one. This is the Heck reaction. Oh, not Heck reaction. This is the metathesis reaction. Oh, I love metathesis. So, with metathesis, this problem looks a lot nastier than it actually is. Now they have displayed it the worst possible way, but whatever. Okay, so that big nasty ruthenium complex you see there, that I believe is a Schrock catalyst. I had to guess it's a Schrock catalyst. Or Grubbs catalyst, but most likely it's the Schrock catalyst. Now you got me second guessing myself. I want to say Schrock is ruthenium. So all we're doing here is alkene metathesis. And there's only two alkenes in here, and it's this branch here and this branch here. So with metathesis, we have two groups, A and B, double bound to each other. So this is a carbon with something bound to it, this carbon with something bound to it. And we take another alkene, and as a first pass, we cut them down the center, and we connect the opposite part. So we get AC, AD, BC, and B double bond D. So these are all double bonds. So in this case, A is this branch here, B is the CH2 group, C is this branch here, and D is this CH2 group. And what we're going to end up doing is clipping this and attaching them together. So we're attaching A to C here, and this is what's called ring closing metathesis, or RCM. So with ring closing metathesis, we're just literally creating a ring. So if we count the carbons, 1, 2, 3, 4, 5. This is a 5-membered ring with nitrogen at the bottom. We still end up with a double bond, so there's your A group, there's your C group, and then the nitrogen has this funky little group coming off of it. And that's your answer. We're also going to produce ethylene, which is omitted from the answer key. But all you're doing with this reaction is you're taking a Schrock catalyst and cutting it down the double bonds. In this case, you're closing the ring. You can easily pull the ethylene out. This is a reversible reaction, so you can drive it towards equilibrium. And that's what you end up making, is this 5-membered ring with a nitrogen in it, and everything else stays the same. How do you name ethers? There's actually two ways to do this. So there is functional class and substitutive. And I always forget which one is which. Yeah, you're welcome. So let me bring it up in my notes to make sure that I'm telling you the correct answer. But I always get functional and substitutive classes confused. One of these is used a lot more than the other. Okay, functional class is the easiest one, substitutive class is the more complicated one. So functional class is the easiest. This one is the hardest. Functional class is the least flexible, so it applies to the least number of ethers. This will work for every single ether. The thing is that we almost exclusively use functional class because it is rare that we will come across situations where substitute class is needed. So for functional class, we name the branches plus YL plus ether. And the name here is not alphabetical, it's by length of the branch. So shortest branches go shortest branches go first, longest branches go last. And we don't care about alphabetical naming. This is purely functional. So for this case, we have an ethyl. So there's your YL. There's the name of your branch. Tert-butyl ether. So our tert-butyl's there. We're going to put this last because it's the biggest one. This contains 4 carbons. This contains 2. If we have 2 of the same type, we would just call this diethyl ether. Now, that said, there's only so many branches that are that simple. And so this is where the substitutive naming comes in. So for the substitutive naming, the ether is treated as an alkoxy. let's kill the stereochemistry. So something like this, there isn't a short name for this branch. Now there's a short name for this ethyl branch, but there's no short name for this ring. Like, we need to define a lot of information. So this is where we would use the substitutive naming. And we're going to have our parent branch here, which is cyclohexane. And our branches here, here's the ethoxy, and here's the chloro. And we'll do these in alphabetical order. So we have chloro, ethoxy, cyclohexane, and we just named the position. So 1-chloro, 2-ethoxycyclohexane. So the reason you would want to go with this is that either your parent chain does not have a simple name like propyl, butyl, sec-butyl, tert-butyl, or you've got some insane amount of detail on this. So let's say that you need to specify the stereochemistry here. So our chlorine goes back, this comes out. We would need the R and the S here to help us specify which one we have. But the big difference with substitutive is that we don't call it an ether. We call this an alkoxy group because we're going to treat it like it's an ethoxide or an alkoxide. It's just a branch along the chain. And this will start showing up more. Actually, it did kind of show up with alkane or aromatic compounds. But generally speaking, this is also the rarest way to name ethers because we rarely ever deal with ethers that are this complicated. So the IUPAC rules exist to address this issue, but that said, in all honesty and practicality, functional class is the most useful one to know because it's the one that gets used the most. If you ever look in the lab manual, if you ever look in any type of chemical catalog, you will see diethyl ether. If you go to Home Depot, methyl ethyl ketone, diethyl ketone, you can go buy these. Methyl ethyl ketone, MEK, is used as an industrial cleaning solvent. So those are actually the more useful ones to know. But again, we have these substituted class because it does show up occasionally. Page 26, 27 on the 1H NMR and carbon 13 for organic 1. Okay, so with NMR, the way you should be approaching this is don't try to go from the spectrum to the molecule, try to go the reverse way. You've got 3 hypotheses here. Now, the one thing I always personally hunt down for when I'm doing 1H NMR are singlets, because singlets are the easiest ones to identify. So here it gives you 3 possibilities. So if I look at my NMR table, I have one singlet with area 3, a quartet, a septet, a triplet, and a doublet. So let's hunt down the singlets first. So this one would have a singlet here. This one would have a singlet here. This one wouldn't have any singlets. So we can pitch this one off the bat, and now we're just down to these 2. So now we look at the integrated area. This has an area of 3. This has an area of 6. Most likely this is the one we're dealing with, but let's make sure we can find the other patterns. So if we look at this one, these 3 would have an area of 6, and they would be a doublet. And if I look at the table, I've got peak 5. That's a doublet with an area of 6. So far, so good. My singlet with area of 3, that's peak number 3. If I look at this one, I would have an area of 1, and it would actually end up being a septet because I have 6 hydrogens that look the same, so I would get a 7, and that's peak number 2. If I look at this one, this would be a triplet with an area of 2, and I have a triplet of area 2, sorry, quartet. Quartet, because there's 3 here, quartet with area 2, and I've got a peak, that would correspond to peak 1, and then my remaining peak, this would be my triplet with area 3, and that would be peak 4. So this molecule is the only one that is consistent. If you look at this one, particularly with this particular atom, I would have a triplet plus a quartet, and I don't see that in the spectrum. Here I would definitely get my triplet. Here I would have a doublet plus a quartet. I'm just not seeing these more complicated splitting patterns like I am in the NMR. So carbon-13 is going to kind of work the same way. So double bromination of pentane. So whenever I do a double halogenation, they're always going to occur on the same carbon, because when I do that halogenation, I end up converting a secondary to a tertiary. So that's likely to occur. That's likely to occur. And there is an esoteric chance that I could get this. But the thing is, I'm doing double bromination, which means that one hydrogen is getting replaced, so the two hydrogens are getting replaced. So when I do my first substitution, this takes one of my secondaries and turns into a tertiary. Tertiaries are far more likely to react. So now I need to consider the carbon-13 NMR. And when I look at the carbon-13 NMR, I've got 3 peaks. Ratios of 1, 2, and 2. So now I would predict how many carbon-13 peaks do I expect to see. Well, this one I expect to see 1, 2, 3, 4, 5, because none of these are related by symmetry. So this doesn't work, it's got too many. And tell you what, I'll also consider this case, bromine here. If I take a look at this one, I expect to see 1, 2, because these are related by mirror images, 3. So this is a possibility if I consider this one, 1, 2, 3. This is also a possibility. Now, got to consider the areas. So these would have, so my peak versus area, we'd have 1 for peaks, 1, 2, and 3. We'd have areas of 1, 2, and 2. Still works, but here's the thing. With this one, I expect 1 to be the most deshielded. I expect 2 to be the most deshielded here. And when I look at the spectrum, that area of 1, that 50 is at 56.2. It's the most deshielded. So this doesn't really make sense, because we need the second carbons to be the most deshielded. So this is the only one that makes sense in terms of the relative areas, the 1, 2, and 2. And it's the only one that makes sense in terms of where the deshielding is. This is the most deshielded carbon from the chemical shifts. So expect the bromines to be attached to that carbon. Can you do stereochemistry like on lecture notes for ring opening epoxide? Hold on. So we're going to be entering 2 conditions. So for the Simmons-Smith, you need to draw both. Same thing with the epoxidation. You need to draw both if stereochemistry is created. And that's the thing to keep in mind, is that with ring up, so something like, if we were to take cyclohexene and we were to do Simmons-Smith or epoxidation, you really only get 1, because this is a meso complex. So in terms of the number you draw the correct number, but also keep in mind when there is more than one stereocenter. So yes, you're creating stereocenters, but are you creating a meso complex? If you're creating a meso complex, you don't have to worry about both isomers. As far as ring opening, it depends on whether you're under acidic or basic conditions. The best way to think about this is SN1 versus SN2. So let's create our asymmetric ether for epoxide. So if we're under acidic conditions versus basic, and I'm just going to put the hydroxide here to indicate acid and base. And what we're going to do to both of these is add some nucleophile. Well, if we're under acidic conditions, this is going to be analogous to an SN1 pathway. What we're going to do is we're going to open up and create a carbocation, and the carbocation is going to go to the most substitute carbon. So this is my first intermediate under the acidic conditions. Because I can get attacked from both top and bottom, I end up creating a mixture like this. So this is going to be analogous to SN1 that I go through a carbocation intermediate, and I end up with a racemic mixture on the most substituted carbon. So I'm going to end up with both the R and the S forms of whatever X is. This is not going to be true of the hydroxide method under the basic conditions. Under basic conditions, I end up having to do this is going to be more analogous to the SN2 pathway. And so what I'm going to get is the X minus attacking from underneath and breaking the alcohol. So when I finish, the nucleophile X minus and the alcohol have to be, we're going to call them trans. That's not what they really are, but that's a term people like to use. We're going to call it trans. So we're going to end up with the alcohol and whatever comes in being trans. And in this case, we only end up with one chiral center on wherever the X adds. So this is analogous to SN2. With SN2, we only ended up with one, if we had stereochemistry, we only ended up with one stereoisomer. This is because we don't go through a carbocation intermediate. With SN1 pathways, we always ended up with a racemic mixture, and we ended up with this racemic mixture because we go through the carbocation intermediate. So I would use those as your analogies here. Basic conditions, this is going to be like an SN2 pathway. You should only finish up with one stereochemistry with whatever the nucleophile is being added. If you go under acidic conditions, you're going to add to the most substitute carbon, and you're going to mixture both the R and the S. Here, you're going to get the nucleophile attaching to the least substitute carbon because we're not going through that carbocation intermediate. So for the copper lithium alkyl reagent, slide 66, I see there are two alkyl groups, but only one of them is attached to the target molecule when reacted. Slide 66. Yes, this is the weird thing about organocopper chemistry, is that there are two there, but only one gets added. So that is correct. To be honest with you, this is really outside. Organocoppers are not something I ever had to work with, so I'm kind of having to rely on other sources for this. I agree with you. I think it's weird that you have to do two equivalents, but it's something to do with the reaction mechanism that goes on to make this reaction occur. I know that if you do two separate, so let's say you had a mixture over organolithium complexes, you would get a 50-50 shot of which one you add it, with some biasing towards steric hindrance around the copper. So I think the bigger groups are more likely to get added. Don't quote me on that, I'm not 100% sure. But this is kind of the difficulty with the organocoppers, is that you do end up losing one equivalent of whatever you're trying to add to making that di-substituted copper complex, and only one ever gets added. You never add both. Yeah, I thought it was two, because every time I read it, it required two equivalents, but you only ever add one, and I think it's probably got something to do with the actual mechanism itself. I'm going to turn the camera off just so I can send some emails. You don't have to listen to me type while I do it. All right, that's the end of office hours. If you get any questions, please feel free to email them in advance. I can definitely answer them at the start of the live stream or answer the chat, or come to the physical office hours from 9 to 11 o'clock on Friday mornings. All right, I will see a lot of you tomorrow.